So suppose you're playing Words with Friends, and the app gives you this nice clue that, hey, your 7 tiles can spell out a 7-letter word. Exactly one 7-letter word. What's the probability that, just by luck, your tiles are shuffled in the right order that spell that 7-letter word? Well, I guess we need to figure out how many different possibilities there are, things that you can, or ways you can put together those 7 tiles. So we've got several counting rules. You've got permutations, combinations, factorials, and then if you've got repeated events that occur with frequencies m and n, then you can multiply m times n, that kind of thing. Well, let's think about which of our counting rules we're going to use. And I'm going to help you eliminate 2 of them. 2 of our counting rules say you're going to take, x of these objects out of a group of n. So you're only using some of them, right? Now, is that the case that we have here? Are we taking some of them out? We're only using some of our letters? No. What's the big thing here? The big thing here is that we're using all of our letters, right? And all of our letters starts to push us towards what counting rule that we used that'll allow us to figure out how many ways there are to arrange 7 letters. Now, combinations and permutations would be used if you're taking, 3 out of a group of 12 or something like that. Factorial. Yeah, so the denominator to our problem, so probability of spelling the right word, the denominator is going to be 7 factorial, which is 5,040. I have a friend of mine whose phone number ends in 5,040, and I call him 7 factorial. All right. So a couple people on the chat, thank you. It wouldn't be a combination because we're not taking some of the 7 letters and not using other ones. All right. You're using all of them, so it's 7 factorial. Now the question is the numerator. Well, there's only one 7-letter word you can spell. There's only one right spelling of it. So what should I put in the numerator? A 1. 1 out of 5,040. Which makes sense. I rarely see numbers or letters in the right order when I have those 7 tiles. Now, if you can kind of put your thumb on the scale a little bit, if you can say, well, I know it has to end in this letter, then you only have to deal with 6 factorial, which is 720. Or if you can figure out the last 2 letters, now it's 120, 5 factorial. So if you can figure out a couple of those letters, you can really greatly reduce the possibilities here. Are we good with that first example here? Call it A. Let's take a, question? Right. Sure. So the question I'm getting on the Zoom is, what if there's more than one word you could spell with the 7 letters? Well, if that was the case, then your numerator would be 2, 3, or 4, etc., depending on how many words there are that you could spell with those same 7 letters. That's why I was careful to say that you can spell a 7-letter word. So meaning one 7-letter word. So does that help out? Was that Z? Yeah, okay. Sure. Let's continue. Now, I can't remember going to the racetrack in like decades, but if you do go to the racetrack to bet on some horses, let's see, where is it? One of the bets you can make is a trifecta. And in a trifecta, you've got to pick the horse that comes in first, the horse that comes in second, and the horse that comes in third. So let's figure out the probability of, or figure out the number of possible trifectas there are for a horse race with 12 horses. So part B, or example B here, with 12 horses in a race, how many trifectas are there? All right, well, are we going to use a factorial on this one? Why not? How come we're not using a factorial on this one? Yeah, you're only picking 3 out of the 12. You're not arranging the 12 horses in orders that they can finish. You're not using all of them. We're only using some of them. And if we're using some of them, that points to one of two possibilities, either combinations or permutations. Now, what's the difference between combination and permutation? Someone remind me. Is she right, Zach? Permutation, order matters. Combination, order doesn't. Good. Thank you both. So, does the order matter here? Am I going to use permutations or combinations? What do you think? Maria?
Permutation, because order matters.
Yeah, order matters. No. It's permutation because the order matters. First, second, and third, if it was blue, green, and yellow, first, second, and third, that's not the same as yellow, green, and blue. I mean, the order does matter. I mean, you want to finish first if you're racing there, right? You're not as happy to finish second, and you're certainly not as happy to finish third. So, yeah, it'd be permutations. So I'd want 12p3. Now take out your favorite tech and find that number. And while you're looking for your favorite tech, I'm going to come over here to Google. No, not to Google, to our class. Let me get to our class to make sure it's there, but I know it is. If you go to the content section in Google and you just search for cheat, it'll come up with this: Google Sheets and Graphing Calculator Commands Cheat Sheet. So this is a copy of a sheet that I'll put in your hands for the test on Monday, and it shows all the different commands you could possibly need to use either Google Sheets or the Graphing Calculator down below to do whatever it is that you might need to do for the test this Monday. And I've promised you repeatedly, and I'm delivering on that promise, that this course is not about Google Sheets. You need to understand the probabilities, the statistics, etc. We do need to get this information somehow, but I'm not going to make you memorize all these types of commands. So I will put a copy of this sheet in your hands. Do me a favor, don't write on it, all right, so that I can keep on using them, giving to you all semester long. But this will be given to you on Monday. By the way, something else to be aware of: bring in your computer, because you're probably going to want to use Google Sheets, and I'll let you use Google Sheets. You can have exactly one window open during the exam. But here's the thing: I'm going to ask you to turn your desk away from me so that I can see your screens while I'm sitting up here. Because I'm going to look and make sure that you're not getting on the chat with your friends, etc. All right, that would be bad. All right, so yes. There's not much work to show other than write down 12p3. All right, and what answer did you get there? 1320. Good, you should get 1320. All right. No, there's not much to show. I mean, if this were an upper level course in probability, then maybe I'd ask people to write down 12 factorial over 12 minus 9 factorial, or 12 minus 3 factorial, that kind of thing. But there's no point in that. It doesn't really help us out. Okay, let's do one last example from section 4.4. Last week, Friday, I was part of a group that went to Beaumont to check out remote learning systems. And, I thought of this experiment. How many ways can a teacher select 8 students from a group of 23 to test a new Zoom product? So again, this comes down to trying to decide the difference between all our different rules for calculating and counting. Let's see if we can't eliminate one of them right away. Are we going to use a factorial? Why not? Yeah, we're not using all of them. We're not saying, okay, how many ways are there to arrange 23 students? That's not what we're doing. We're picking a subset out of those. So if you're picking a subset out of those, the question is, does order matter or does order not matter? On the chat, let me see some numbers on the chat here. Does order matter or does it not? Are we using permutations or combinations? All right. All right, so it seems to be pretty unanimous. Looking like combinations, so good job. So it's going to be 23C8. And again, use your favorite tech. Do you want to use your graphing calculator? Do you want to use Google Sheets? And whenever you're ready, give me the answer. Yes? There's a lot of different possible groups there. Yes, thank you, Zach. Mike, oh, I'm sorry. All right. It's tough sometimes to recognize people underneath. All right, thank you. Appreciate that. How are we doing with this one? You okay with that one? So, I mean, this isn't a total comprehensive study guide, but it's trying to bring you up to speed, up to where we're at. So, let's keep going. And I'm going to keep going with section 5.1. We'll do problem number 10. And let me find what page it is. Say again? 5.1. So it's going to be on page 215. And lots of people active in the chat today. I appreciate that. And once again, to repeat myself, you can use and will use, I would think you'd want to use Google Sheets. And let's think about this one, problem number 10. Actually, let's think about problem number 9 first. No, not 9. Where is it? 11. Because in this section, I introduced probability distributions. Is problem number 11 a probability distribution? You guys are working too hard. Is it or is it not a probability distribution? I'll give you a hint. If you're adding, you're barking down the wrong trail.
I don't think so because there's 3 options.
That would be if it was a binomial probability. we'd have to have two outcomes. But there is something wrong here. Does anyone see it? Let me check the chat here. Ah, there we go. Well done, Aisha. It's not numerical. Remember, in order to be a probability distribution, this has to be numbers. All right? And if it's not numbers, that's it. It's just not a probability distribution, even though it adds up to 1. So let's look at problem number 10 here. And for problem number 10, well, you need to check, first of all, that this adds up to 1. So that's one thing. And if it does, well, all these probabilities are between 0 and 1, so it looks like a probability distribution. And assuming that it is, then we're going to want to calculate the mean and standard deviation. Now, I'm not sure how you want to do that. But what you have to do to first find the mean is do x times p of x for all of these. So do all those multiplications, and then add up those products, and that's going to be the mean. And that's the easy part. Standard deviation gets more involved. Now, you pick your poison. You can do that with pencil and paper. You can do that with a graphic calculator. You can do that with Google Sheets. You tell me what your vote is. What looks easiest? Yeah, to me, it's a no-brainer. It's Google Sheets. Because all you do is type in a command or two, and then boom, let it do all its magic. So, my homies there. All right. One vote for Sheets. I'm hoping that the rest of you are on board as well. Now, if you pick up my my section 5.1 link from class the other day, that should take you to a web page where I've already got this table input for you. And let me just delete a few things here for us so that we can calculate that stuff on our own. There you go. So if you open up the link from section 5.1 from the other day, you can get that page. It's actually sheet 3, I think. Let me put that into the chat for those of you at home, and for those of you here, I'll put it in D2L on the announcements page. So, actually, you know what? It should be the same link that's here. So this should be able to open up, and you should be able to get back to this. Probably what a good idea would be for you is just to take and copy this and paste it to a new Google Sheet. Paste it, open up your own fresh Google Sheet. Maybe save it as 5.1 or 5.1 part 2. Or if you want, I don't know if you guys have noticed this or not, but you can have many sheets associated with one Google Sheet. So here's what we first started out with on sheet 1. Then the other day I used sheet 2. And here I am with sheet 3. So one way or another, I hope you found your way to a place you can work on this page. All right. And so then this column, to create the mean, you're just going to do x times p of x. Before I do the x times p of x, what does my Google Sheet command start out with? Equals. You got to start with equals, and then x asterisk p of x. So it should look like that. My guess and my hope is that when I press the enter key, it's going to ask me, gee, do you want to do that all the way down? Let's see. And the answer would be, yeah. You want to do my work for me? That's fine. I'm good with that. So I'll just check that. If that wasn't working for you, you can click this box and drag it down. Now I've already got 2.5 down here. That's the sum of all those values. So what is that 2.5 telling me? Anyone? What's that 2.5 represent? That's the mean. That's your expected value. That means if you did this experiment again and again and again, hundreds of times, your average value would be 2.5. It'd be right there in the middle. The harder part is to get the standard deviation. And so for this, we'll start out with equals, like all of our commands, equals p of x, which is this, times parenthesis x. Now I'm not going to type in x. I got to type in the value of x. So I'll click this cell. And here, let me remind you, when you type in mu, you want to type in the value of mu. Don't get fancy. Just actually type in the number, 2.5. Don't click down below and use the total that I have there. I'm not going to bother explaining why. Just listen. Raised to the second power. So that should be your command here on this first line, like that. So when you press enter, you should get 0.91 or 19375. People at home, are you getting that? Is there anyone here that's getting stuck? They're like, it's not coming up for me. And this is your chance to get some help. So reach out if you need it. Okay. I'm going to click autofill there. No, I don't want to give feedback. All right. And thanks for those who reached out in the chat. Now, I'm going to sum this up. But when I sum that up, what's it going to give me? Is it going to give me my standard deviation? It's going to give you your variance. So you can either type equals and then sum. And in the sum, you want to sum up all that stuff. Or you can give it fancy and just copy that formula over here. Either way, you're fine. But now I need to get the standard deviation. So how do I get the standard deviation once I've got the variance? Square root it. Good. So it's going to equals SQRT square root of this thing. Bam. Like that. Okay. Thanks, Z. So there's your standard deviation. Perfect. Yes. Variance is the sum of that. Yep. Okay. Now we don't use variance much. It does measure variability. The unfortunate thing is that it's in units squared. So if this were number of girls that you can expect amongst 5 babies, then the variance would be in girls squared, which sounds interesting, but I can't really make sense out of it. So you take the square root of that, and now your units are back in the original units. So 1.1 girls would be the standard deviation. That tells you how much spread there is in the data. Now, if you scroll over a little bit, we've done this stuff, but I'm not sure I've used the name very much. It's called the range rule of thumb. And the range rule of thumb helps you decide what's typical and what's not typical. So that's going to be anything within 2 standard deviations of the mean. So let's decide what's typical. What's 2 standard deviations away from the mean? So I'll do equal. Oops. No, I don't want to do that there. Yeah. Undo. Come down here. Equals. Now I'm actually going to type in the mean. 2.5 minus 2 times sigma. Well, where am I going to get sigma? What do I mean by sigma? That's a standard deviation. So I'm just going to click down here because I don't feel like typing in 1.11623, etc. So I'm just going to type that in. That's the mean minus 2 times the standard deviation. And then I got to do the mean plus 2 times the standard deviation. So 2.5 plus 2 times sigma, which is back down here again. So I'll click that again. There you go. So that's our range rule of thumb applied to this particular problem. Okay, looking good. Now a follow-up question would be, what are there any values that we can get here that are atypical, that is unusually high or unusually low? So I'm just going to squeeze this over a little bit. There you go. Are there any possible values for our variable that are significantly low or significantly high? I got to vote for 0 and 5. Do you guys agree or disagree? Well, let's take a look here. So, so we got about 0.27 and 4.73. 0, 1, 2, 3, 4, 5. So the range rule of thumb said, okay, we're going to give you values starting here at around 0.27 to 4.73. That's what's going to be inside of our range rule of thumb. So effectively, that includes these. Does it include the 0? No, 0 is not part of that. So 0 is significantly low, and 5 is significantly high. These would be unusual results if you got them in your experiment. They just typically don't happen. That's all. That's all it's saying. But that's applying to your range rule of thumb. Which data was used to calculate standard deviation? Problem 10. So I'm just going off of what we just calculated here. So let me go back to Google Sheets here for that. That's this standard deviation. So from problem 10, page 215. All right, cool. So that's 5.1. So a little review from you on 5.1. No. No. So I guess a question that, or I guess something you are going to have to memorize is those formulas for the variance and for the mean. Okay. Those two you'll have to remember. Okay. Let's continue. And I think we're getting to a fun part here. Let's see here. So let's work with section 5.2. 5.2 is what we did the other day. 5.2. And I'm going to start by giving you some example problems that you're going to see in the homework. We really didn't cover the other day just because of time constraints. But we're going to take the time to cover them now. And it's just deciding whether or not something is a binomial random variable. So let's take a look at that. So let's see. Now, to decide if something's a binomial random variable, there was a word that I used that helped us. Does anyone remember what that word is? Yeah. So a binomial random variable fits. And let's remind ourselves what that acronym relates. What's the F part stand for in this context? No one? Good. Fixed. Yep, fixed number of trials. I stands for, thank you, independent. T stands for two outcomes. And finally, S stands for the same probability of success throughout the trial. Same probability of success through the trial. All right. Looking good there. Let's test out a few examples and see if some of our data fits. All right. We'll start with problem number 5. This is on page 227. So let's see. Yeah. Number 5, page 227. And in a Pew Research Center survey of 3,930 subjects, the ages of the respondents are recorded. Now, let's run through the acronym here. FITS. Are there a fixed number of trials? Yeah, 3,930. So we're fixed there. Are they independent? Well, assuming that this is a Pew Research Center survey, I mean, Pew is a very reputable organization. They're not just going to pull out their friends and their relatives. They're going to do a nice random selection of people from throughout the country. So that would give us independence if you're just picking people at random. Then what? What comes after that? What's the next thing on my list of acronyms? 2 outcomes. Are there 2 outcomes for this kind of experiment? No. There's a lot of ages, right? So there would definitely not be just 2 outcomes here. So yeah, you're out of luck on that one. So you can stop here. It doesn't fit. So F-I-T-S. So that one worked, that one worked, that one didn't. So we're out of luck on that one. What if we change things up? So instead of asking people their age in problem 5, let's take a look at problem number 6. And problem number 6 says, in a Pew Research Center survey, 3,930 subjects were asked if they have ever fired a gun, and the responses recorded consist of yes or no. Well, let's see. We still have a fixed number of trials, independence. How about the 2 outcomes? Got that. And the same probability of success is guaranteed to us by what's called the 5% rule. We've talked about that before. I'll circle back and talk about that a little bit more after we do problem number 10. So problem 6, F-I-T-S. So yeah, this is a binomial random variable. Okay. Let's keep on going. We'll do problem number 8 next. The Y sort. That's okay. Go with mine. Number 6 was just all yeses. I checked all F-I-T-S. They all got a check mark. So it was a binomial random variable. So let's look at problem number 8 here. The Y-sort method of gender selection developed by Genetics at IVF Institute was designed to increase the likelihood that a baby will be a boy. When 291 couples use the Y-sort method and give birth to 291 babies, the genders of the babies are recorded. So, do we have a fixed number of trials? Yeah, got that one, 291. Are they independent? Yeah, if you and your spouse have a boy, that doesn't affect the probability that somebody else has a boy or a girl. Those probabilities are going to be independent. 2 outcomes, yes, boy and a girl. And same probability of success. Now, we don't know what that probability is, but that's going to apply to all those couples. I mean, even if it had no effect, then the probability would be 50-50. But that probability is going to be the same from one couple to the next. So this one fits. So FITS. There's a good chance. Let's take a look at problem number 10. Now, let's see, FITS. We're going to do 10 and 10 prime. So I'm going to modify problem number 10 after we look at it and see what happens with my modification. So we'll do the easy part of problem number 10 first. It says 10 senators from the 116th Congress are randomly selected without replacement, and the number of terms that they have served are recorded. So let's work our way through the list. Is there a fixed number of trials? Anyone? Be brave. Mike, you seem to be struggling with this part. Problem number 10. There's room a little closer. If you're so. Oh no, it's okay. You're socially distanced if you want to go up there. But if you're comfortable back there, that's fine too. And I appreciate you being responsible about the social distancing stuff. Thank you. Let me see if I can't make this a little bit bigger for you. All right. So, fixed number of trials. Are they independent? Not really, because you're sampling without replacement. And I'll get back to that in a minute. But even more devastating to this being a binomial random variable is the next part, the T part. What's the 2 parts stand for? Or the T, yeah, I guess I already gave it to you. There's 2 outcomes, right? Are you going to get 2 outcomes when you ask them how many terms they've served? No, you're not. You get all kinds of crazy answers. I think Strom Thurmond was the longest serving member of the Senate, and he died in his 90s. He served like 6, 7, or 8 terms. I don't know what, but it was a lot of terms. So, yeah, definitely you can get a lot of different answers there. So we can stop. Once you see that there's more than 2 possible outcomes, that's it. It has to satisfy all of these. So once it doesn't satisfy any of these, skip it. So yes, no, and no for here. And does it really matter here? No, not really, because it's already failed things. But what if we looked at the number of women in the 110th Congress? And here's a little subtlety that I want to point out, something that we've taken advantage of. We're going to sample 10 women from the Senate, or 10 people from the Senate. Now, I don't know the actual makeup in terms of gender in the Senate, so let's just assume that there's 20 women and 80 men. I don't know if this is accurate in any way, shape, or form, but I do know that we don't have gender parity or anything close to it, I don't think. Now, if we're going to sample 10 members of the Senate, does it make sense to sample without or sample with replacement? Would you sample somebody, put them back in, and sample them again? No, it doesn't. So without replacement, and count the number of women. Okay. So let's do a little experiment. Let's take out the first person from the sample and look at the probability that she's a woman. So probably that the first one is a woman is 20 out of 80, right? Or 20 out of 100. But here's the thing. We're sampling without replacement. So that person gets taken out, and that's it. They're gone from the sample forever. What's the probability that the second one is a woman, given that we've already sampled the first one, and that was a woman? 19 over 99. And then the third one? 18 over 98, and so on. So what's happening to these probabilities? Are they staying the same? No, they're changing, right? And so that violates the S part of our fits. They can't change. You have to have the same probability from one to the next. So now, we can get away with that if the sample size is small enough compared to your population. What was our threshold for small enough? How small did it have to be? Had to be 5%. 5% of 100 is 10. Or excuse me, is 5. Well, we've got 10 people that we're trying to sample here. So this fails our 5% rule. So we got to throw this out. We can't use this. It doesn't fit. That's because sampling without replacement leads to dependent events. But there's our 5% rule. If the sample size is less than 5% of the population, you can treat the events as if they're independent. Now with our reworked example of problem number 10, it still didn't fit because that probability changed from one draw to the next. And it didn't satisfy the 5% rule, so we lost on both counts. So if you're going back to problem 10 prime, that one works, this one doesn't. And it doesn't matter on this one. These two failed. Okay. Now, a lot of times, surveys on the national scale are based on a couple thousand voters. So, let's see. Suppose you had 2,000 voters and you draw a sample, or you're going to draw a sample size of 2,000 out of all the eligible voters here in the United States. And for sake of argument, let's just assume that there's 180 million registered voters in the United States. So, okay. Let's say you pick one of those people out. And You looked at another person in this pool of registered voters. Now you're talking about 1,199 out of 179,999,999. The probability has changed, but has it changed by that much? No. You'd have to be like a forensic accountant to notice the difference there. You're just not. So if your sample size is small enough compared to the population, and truth be told, this is not an exactly fair example, but it gets the point across. If your sample size is less than 5% of the population, you can treat it as if they're independent. You don't have to keep on adjusting this down. We'll just say, okay, well, it's 0.003 to the whatever power, that kind of thing. So you don't have to do that kind of corrective measures thing. Okay, thanks for hanging with me through that one. Now, here's the fun part. Here's your reward for sticking through this with me. And I'm going to need a volunteer for this. Actually, maybe 2 volunteers. Any volunteers? All right, come on up. Anyone else? Mike, come on up. All right, so here's our data. Woohoo! See, you should have volunteered. I told you it was in your best interest. All right, so let me open this up. It's a fresh bag. Only $8 at Rite Aid. All right, wasn't that bad, I don't think. Let's see. There we go. All right, so I'm going to pour this out on a plate for each of you. There you go. So there's one for you. And you can take it back to your seat if you want. Now, I'm not sure if you're aware or not, but there's an urban legend that surrounds a particular color of M&Ms. Does anyone know anything about that one? Is there a color that's desirable? It goes back to like the 70s. I actually looked it up on the other day. But basically, to be polite about it, the green ones are supposed to act like an aphrodisiac. So give it to your love interest if you believe that thing works. All right. Now what we want to do is we're going to conduct a binomial experiment. We're going to see, well, what's the probability of getting so many green M&Ms out of the ones we have. So let me separate these into different colors. Now the color composition of M&Ms has changed a lot over the years. For a while they took red out because there was a rumor that red ones had red dye number 5, and that was really, really bad. So red's come out, blue's been in and out. And the composition in terms of the number of colors also changes based on where the plants or where they're manufactured. There's 2 plants that manufacture them. One is Hackettstown, New Jersey, and the other one is Cleveland, Tennessee. Yeah, that was what I thought. I'm like, wait, not Cleveland, Ohio? Cleveland, Tennessee. I don't know. I don't know why Cleveland is such a cool name that Tennessee wanted it too, but they do. So the composition changes depending on where your plant is. So my homies, here's your assignment. Count up the different numbers of colors here. And I'll get you some probabilities involved. So we can do a binomial random and variable experiment here. And then the instructor gets to eat the data. I don't know. I didn't work out today, so maybe I shouldn't. All right, let me zoom out a little bit so you can see the blues and move these around so we can count the oranges. So let's see. Red, green, orange, brown, yellow, and blue. So 5, 6, 3, 6, 9, 11, 8, 8, 6, 8 again, and blue 5, and 4 is 9. Okay. And I hope that you're agreeing with me. Are you guys getting the same numbers? All right. I'm not sure what that last part is. So let me share with you a Google link for this stuff. Where is it? No, not there. Where's my M&M data? Oh, nuts. All right. This is feeling like it's starting to take a little too long, so I might just bail and do a different problem. But you guys are free to eat the data once you've got the numbers that I've got. Let's see, docs, M&Ms. M&Ms, there we go. So let me scroll down here and go to a blank observation. So these are the probabilities involved, depending on the plant that you are. Assuming that, like us, we get ours from Hackettstown, New Jersey. Most of these have a 1 in 8 chance of coming up, but a couple of them have a 1 in 4 chance, like the orange and the blue. And they do a lot of testing to decide the makeup of these things. I don't know why, one would be much different than the other, but that's okay. That's not me to decide. So let's list our observed. There was 5 red, and I got 6 green, 11 yellow, 11 yellow. No, not 11 yellow. I'm sorry. Orange, I had 11. Yellow, I had 8. Blue, I had 9. And brown, I had 8. Equals sum. Let's find out how many I had all together. I had 47. So we're going to treat this as a binomial random experiment. We're trying to figure out, how many green ones you should expect. So let's see what we did. See what we get here. So the probability of a green one is 0.125. So probability of a green one is 0.125. Now, is this a binomial random variable? Well, let's think about it. I've got 47 M&Ms that I pulled out, so that's a fixed number. Are they independent? Well, let's assume these 47 are from the billions of M&Ms that get produced every year. So that's certainly less than 5%. So you're going to have independence. So fixed number of trials, independence, 2 samples, or 2 outcomes. Do we have 2 outcomes? Kind of, yeah, if you're thinking green or not green. Those are our 2 outcomes, green or not green. So we're okay there. And same probability of success? Well, yeah, we get that from our 5% rule. We're going to assume that they're the same, even though, okay, we took a few out of the billions that we get. Now, the nice thing about working with the binomial distribution is that you don't have to do all the extra work that we did for our first problem in terms of trying to find the mean and standard deviation. So that calculation we did with our first problem, and I think I might have started recording this video after we did that. Let's see, right here, we do x times p and then add it up. P times x minus mu squared, add it up, get the variance, etc. Those calculations, that's a lot of work, isn't it? Even with Google Sheets. Thank goodness we're not doing it by hand. But if you have a binomial random variable, there's a nice shortcut. And that shortcut is that mu equals n times p, and sigma equals the square root of n times p times 1 minus p, or you can write it as n times p times q, as long as you realize q is 1 minus p. So how many green M&Ms should I expect if I've given myself, what was it, 47? So let's take a look there. Let's just double check back. Yeah, 47. So the mean is going to be 47 times 0.125. Should be a little bit less than 6, I'm guessing. 7.875? Oh, 5.875? Awesome, thank you. Now sigma is going to be the square root of 47 times 1.25 times q. Well, if the probability of getting a green one is 1 in 8 or 0.125, what's the probability of not getting a green one? 7 in 8. And 7 in 8 has the decimal of 0.875. So let's figure out the standard deviation there. All right, so I'll clear this out. Clear this out. So 47 times 0.125. There's my mean. And then the second one is square root of 47 times 0.125 times 0.875. And I don't need that right parenthesis there. There we go. So about 2.267. Okay. Not bad. Let's apply the range rule of thumb to this data and see, well, what would be unusual and what would be, unusually high or unusually low? Where do I set that boundary? Now, let me give you a reminder and then a suggestion. The reminder for the range rule of thumb is this: mu minus 2 sigma to mu plus 2 sigma. So I'm going to need to subtract 2 sigma from both of these. My mean was the 5.87. This is my standard deviation. If you can do that on a calculator, it might be a nice idea to maybe store this value. Bless you. So you can help yourself out if you store that value. I'm just going to hit the store key and put that value in X. That way I can make my life a little easier. I'll do 5.875 minus 2 times X. So that's the lower end of things, about 1.34. And on the upper end of things, I want to do that calculation again, except this time I want a plus there. 10.409. Now those are the exact values for my range rule of thumb. But what does that translate to practically? So 0, 1, 2, 3, 9, 10, 11. So what would be significantly high and what would be significantly low for this kind of an experiment? Yeah, anything below 1.34. So that would be these two. Anything 11 or higher. All right. So anything between 10 and 9 would be okay. That's kind of what you expect. And rarely, when I do these kinds of experiments in my classes, do I ever find anything that's outside that range. They're really pretty good about giving us a good mix. And in this case, we got 6. That's pretty square in the middle. That's almost exactly what you would expect, right? Is getting 6. And we got 6. So not bad. Okay. I guess the last thing I'll do here is give you a reminder on how to calculate binomial probabilities. So let's calculate the probability of getting, say, 12 green M&Ms. So we've already established that that's a binomial probability, the number of M&Ms we get of a particular color. Doesn't have to be green. Probability that x equals 12 in this condition, we're going to assume that probability of success is 0.125, that n equals 47, and we want the probability of having 12 successes amongst these 47. So how likely is that? Well, that's going to come from binomial distribution of, I think it's x then n, right? So it's going to be 12, 47, 0.125. And then, does anyone remember what we put here? False. Now you can do that on Google Sheets or your graphing calculator. The command on your graphing calculator is going to look a little different, but it's on that sheet that I have for you, that cheat sheet. Let me do it here. So equals binomial distribution of 12, 47, 0.125, false. And it should probably be a really low number. Yeah, less than 1%, 0.007, which makes sense. Okay, I hope that brings you up to speed on all that stuff. That was a pretty good comprehensive review here. Any comments or thoughts from my homies? All right, because I'm going to stop the recording here and I'll post that when I get a chance. Good luck. Your test on Monday will cover 4.3 to 6.1, although we're not done here yet, so hang tough.